Hi guys, let's look at the row shear failure of the diode connection for this particular member here. To understand this equation here, there are a couple of things needs to be cleared through. First one is the A critical, so that is the critical distance between either between the diodes or the edge distance. So the code gives a very conservative approach, saying that if you have a closely spaced downs, which is looking at here, or if you have a very long edge distance, and your critical distance would be just simply the distance between the downs, because that is the embedment depth, effectively the very minor embedment depth for the downs. All right. So, and next thing is your NFI, that is your number of fasteners in a row. That's the in-row fasteners, okay? So because this formula over here, RSI, that is looking at one particular row. So this is just one row, remember. And if you have more downs, that gives more row shear resistance because more downs and more embedment depth and more timber fiber behind in front of the downs to stop the downs pulling through. So that is a good point, and increasing the row shear resistance by using more downs in a row. Okay, and the next thing is this factor here, KLS. So this is the load stress factor. So what does it mean is this is something to do with the stress profile of the of the downs basically. So if you were looking at, sorry, let me rephrase. So this is the stress profile at each row location of each downs. So if you're looking at cross section over here, and we take a particular point over here. So assuming this is one down, one row of the downs, okay? So for that downs over here, and I've got a stress coming on my left hand side, right? And also stress is coming right on my right hand side because I'm trying to shearing off this. There's a timber fiber around this down. The timber fiber is, excuse me, the timber fiber is trying to stop the tail pulling through. So causing stresses at both sides of the down. And in this case over here, and if you got timber fibers far away from this dowel here, so this is the end distance over here, and your stresses over here is what is like near zero, and over here is like high concentration. Stress concentration is like an old peak at this point over here, right? So if we were drawing this stress profile along this line here from edge to edge, okay? And if a down is one down, two downs, and three downs, okay? And then your stress profile would be essentially looking like this, right? And particularly at the end area, end region here, you can say our stress is from zero increasing up. And they can say if you take average of that, it's going to be 0.5 basically, something like that. But the code says I'm going to take a conservative approach. I'm going to use 0.6 because this is a conservative. So in this case, KLS is 0.6 on the outside. So that's where the 0.6 came from. And internally, because you've already got the very high stress concentrations at each location of the dowels of the rows, so it's typically saying that I'm not allowing any stress reduction at internal spots. It's all going to be 1.0. So no change, stress profile, no change. So in this case here, if you were saying that I'm going to do it accurately, so I can say my externals are 0.6 and the 0.6 internals are 1.0. So I got essentially my overall shear reduction, my overall shear resistance to be reduced by 40%. That's what it means by using 0.6. Whereas if you have more rows of downs, you can say, you can arguably say that I'm going to just use 0.1 because I don't want to penalize much of my internal downs, and it can say I'm going to just have 2 rows of downs. Okay, and we're looking at the plan view. Okay, 2 rows of downs, and I have multiple rows of downs internally. I'm just using because my internal downs are taking much effective resistance. So I'm going to say I'm going to use 1 for all of that and disregard 0.6. Okay, that's the KLS factor. This is quite important just to understand when you're going to use 0.6 and when you're going to use 0.1. Okay. And next thing is there's a 2 over here, number 2. So what does that mean is the particular row, because RSI is looking at a particular row shear. And every particular row, I have 2 shear planes, right? It's exactly like the knife plate you have, or the bolt in shear. You have a bolt in shear, you have a bolt in shear, you have 2 shear planes. That's what it's telling you. Because you got to, at this case over here, the 2 means 2 shear planes in that row, in that particular row here. So this number is always going to be 2 if we are looking at one single row shear. Okay. And next is once you've got all these numbers in, we can just plug it in and we get our RSI value here for 1 row only. And then we substitute this 1 row factor over here, and we're going to be using how many rows do you have to resist the shear, because more rows is going to have more resistance. So this is a helping factor. Okay, it helps. If you have 3 rows, it's going to simply times 3. That is increasing your overall row shear resistance. And then you go to your load duration factor 0.1, surface factor 0.8, and then eventually it got your row shear resistance. That's it. All right, thanks for watching.